Professor Filipuk. Could you hear me?
Yeah, can you hear me?
Could you share your screen? Okay.
I'm sharing. Is it?
Because, okay.
Is it sharing or not?
No.
Is it sharing?
Okay.
Hello, can you hear me?
Some
Hello?
problem with the microphone.
Can you hear me? Okay, so can I start? Okay, so can I start? Yeah. Okay. So hello to everyone. Thank you very much to the organizers for this opportunity to present a talk online. So I wish you are having a very nice time in Spain. Okay, so you can hear me? Do you hear me?
Sorry, we have some technical problems for the audio.
Okay, so let me once again let me thank the organizers for this opportunity to present a talk. So I'll be speaking about orthogonal polynomials and
we have some problem with the audio. We don't hear.
But on chat,
No.
someone is writing that you can hear.
Could you wait for a minute?
Yeah, yeah. Is it solved?
Okay. So
can you hear me?
Just wait for a few minutes. I hope that they will fix this problem very soon.
So is it okay already to speak? Yeah. Can you hear me? Okay. So is it okay to speak? No, not yet. Okay.
Sorry for this problem. Maybe we have the solution.
So already okay?
The problem is for the audio in the auditorium, but maybe the organizing committee solve these inconvenience, and I hope that in few minutes we can listen Professor from Poland. I hope so. No? Sorry for...
Okay, can you hear me?
Okay, let's start.
So are we starting, yes?
Okay, it's a great pleasure to announce Professor Filipuk from Poland, and her talk, the title of her talk is Orthogonal, Polynomial, and Painless equations. Please start. Thanks.
Okay, thank you very much, and thank you very much for this opportunity to present a talk online. So I shall just be very brief. So I'll speak about connection between orthogonal polynomials and nonlinear differential equations. So as you know, orthogonal polynomials appear in a wide range of applications in mathematics and mathematical physics. So they satisfy the three-term recurrence relation. And if some weight function depends on the parameters, then also recurrence coefficients and polynomials would also depend on this parameter. So an and bn would be called the recurrence coefficients, and I would be interested in the behavior of these recurrence coefficients for certain weights. So for monic orthogonal polynomials, we have essentially the same recurrence relation. So well, I mean, the recurrence coefficients would be the same, but the three-term recurrence relation is a little bit different. So let me speak about Painless equations. Maybe you are not familiar with them. So this is one of the examples of the Painless equation, and this is equation with which I will be dealing here in this talk. So as you can see, this is a second order nonlinear differential equation, very complicated. So in general, it is assumed that this equation is over complex numbers, and also alpha, beta, gamma, and delta here are arbitrary parameters, complex parameters. So those equations were found by Painless and his students, and they appear in a wide range of applications in integrable systems, in random matrix theory, and in many areas. And sometimes recurrence coefficients for certain weights are related to some Painless equations. There are 6 Painless equations. They are reducible, and sometimes they're called nonlinear special equations or transcendence. Solutions are called Painless transcendence. So usually, if you use the technique of ladder operators for orthogonal polynomials, and also combine with some kind of Toda type differential in different systems, so sometimes you are able to see that the recurrence coefficients satisfy these Painless equations. So sometimes discrete, sometimes also differential. But usually those equations for the recurrence coefficients, of course, they are not immediately Painless equations. So one needs to identify with the canonical form. And this is a very difficult problem. and this is called the Painless identification problem. And actually, those equations have very nice geometry. So this was studied by Akamoto, and he proposed a kind of a very interesting notion of a space of initial conditions. So I'll just explain in a second what this means. And so on this space of initial conditions, Painless equations or Hamiltonian systems equivalent to them become regular. And this space of initial conditions can be very nice. It can have some symplectic form. And actually, this space includes a lot of information about differential equations and symmetries. So let's have a look at this example. So this is the deformed Laguerre weight, which was studied by Min and Chen. And this is given by this weight. So as you can see here, this part is just the usual Laguerre weight, but here we have some deformation. So theta is a Heaviside function. So certain auxiliary functions Rn and Rn small, which come from the ladder operators, satisfy the following, so are related to recurrence coefficients by this formula. So essentially they are recurrence coefficients, but a little bit kind of shifted. And auxiliary functions satisfy this second order differential equation. So although in the paper of Min Chen, they already kind of found the connection to the fifth Painless equation, it is kind of it was interesting for me to have a look at this system from the point of view of kind of regularization of the system and from the point of view of the space of initial conditions of Okamoto. So let us give some very few details about what I do. So this is okay. So I'm going to use a certain notion from algebraic geometry. So this so algebraic geometry notion is a notion of blow up. So you consider your initial system in Q and P coordinates, but then you can compactify your space, and now you are considering your space like projective space. So you're introducing also those coordinates. And so since solutions of the Painless equations are meromorphic, so we want also to understand what is happening at infinity. So we rewrite our system in new charts. And if we see that the right-hand side becomes 0 over 0, so we need to resolve this kind of indeterminacy. And resolution of such points, so geometrically, this is just inserting a projective line over a point, but algebraically, this is just a change of coordinates. So we're introducing, instead of say coordinates xy, we're introducing two new charts, uv and uv big, and again see what is happening with our new systems, whether they have any other points of indeterminacy. Okay, so let's have a look at what we have. So if, for instance, if we, for instance, we return back to the system, then we will see that, so for instance, okay, so if I'm introducing now Rn and I'm replacing Rn by Q and Rn by P, so so first you you would be able to see 4 initial points of indeterminacy, and also you will see the fifth point in some kind of infinity chart. So the first points of indeterminacy can be resolved just after one blow up, and the final chart systems regularize. So in other words, as you can see here, if you substitute V capital is 0, then the right-hand side already doesn't have any further points of indeterminacy on the exceptional divisor. And also you can see that the form of the system is kind of very similar. Also the same is happening when you resolve the third and the fourth point. And actually here you see that just applying very, very easy transformation, Möbius transformation, you'll just get the fifth Painless equation, which was given here, if you remember. So this Painless equation for the function u with certain values of the parameters. And this is the same for kind of for all charts. The resolution, if you remember, there was a fifth point. So the resolution of the fifth point is a little bit more complicated, and you need several consecutive blow-ups. So you first see this point, then again you see this point, and so on and so forth. So in general, this process for differential equations may not terminate, but for Painless equations, somehow this is almost always finite. Okay, so and also there is some intermediate local transformation which I do, which is due also to Takana. So this is some local change of variables, and the final system finally looks like this. And if you compare the structure of the system again with, say, with these systems, then you again see similarity. So therefore, just using a very, very similar Möbius transformation, you again get the fifth span wave equation for these parameters. Okay, so so from your initial system QP, you use this birational transformation in order to get this system. And the inverse transformation is also given here. So we also have certain Riccati type solutions for these special values of the parameters of the fifth span equation. So it means that we're dealing with the so-called classical solutions of the fifth span equation. Now, if you take our fifth span equation and you are taking this replace, so you replace t independent variable by s using this kind of transformation, and you're considering what is happening at infinity as n tends to infinity. Then you'll see that the first coefficient here in this kind of formal expansion with respect to n satisfies satisfies the so-called Painless 34th equation. And also, what we also so here, as you can see, so all those final chart systems are rational in general. But now the question is, like you started from. Is it possible kind of to regularize the system and find some systems with polynomial right-hand sides? And also, if the systems are with polynomial right-hand sides, you might ask very easily if the system is Hamiltonian or not. So one more blow up would give you the polynomial right-hand sides, and also you can check that those systems would be Hamiltonian with such nice Hamiltonian functions. So and then you can pull back and recalculate that also those systems here would and here would also be Hamiltonian with a little bit different kind of symplectic form, and they can be written down in this way. Of course, if you're just looking at this system, you cannot very easily tell whether the system is Hamiltonian or not. And using this kind of geometric approach, you easily can write those systems in this way. And the same is happening for H2, H3, and so on. So here I've given just explicitly those examples of the Hamiltonian functions and corresponding systems. So here H8 Hamiltonian is a little bit, as you can see here, is a little bit longer. So LaTeX even kind of cut the formulas. So yeah, and the initial system is also, so if you trace back all the transformations, all those birational transformations, you'll see that also your initial system is also Hamiltonian with respect to this form. So just have a look at this system, have a look at this initial system. So Rn big is Q, Rn small is P. So of course you cannot tell just immediately from the system that it can be written in such a nice way. So in other words, we have proved that the initial and final charts differential systems can be written as Hamiltonian systems. And now, so just one more problem is that, so we have the so-called background transformations of the fifth spelling equation. So so it means that we know if we know some solution with certain values of the parameters, we can find another function. So this is written in this way, which gives again solution of the fifth spelling equation with new values of the parameters. So in other words, you know how to generate new solutions of the Painless equation, given if you know some initial seed solution. And and actually, if you change the parameters n to n plus 1, then you'll see that the new solution would satisfy kind of this formula. And from this formula, it's very easy to find this kind of discrete system. So this is known as one of the Painless equations, discrete Painless equations, and so in the theory of Painless equations, discrete equations are also very studied in in some details. So yeah, so this just gave you information how to transform, so how to get the system if you know those kind of final chart systems. So yeah, so what I wanted to say is that this kind of combination of orthogonal polynomials of differential equations, so this procedure of blow up and from algebraic geometry and regularization sometimes gives you very nice results. And in particular, it allows you to solve the so-called a Painless equivalence problem. So so how to identify your given system for the recurrence coefficients with one of the Painless equations. And also as a kind of in addition, you get very nice kind of Hamiltonian formulation, and once you know the fifth Painless, the recurrence coefficients are related to the Painless equations, and then you know how to construct also some discrete systems for the recurrence coefficients. So basically, this is it. So thank you very much for your attention. So are there any questions or comments? Thank you.
Are any questions? We try and interact. There are no questions. Okay, thanks again.
So thank you very much and enjoy the conference. So see you at some point somewhere.
Could you repeat? Okay, we say bye.
Bye.
And we thanks again.
Thank you. Thank you.
Okay, thanks again to Ben, Anna, and Galina and Marina for this session. It is closed, officially closed. Okay, thanks.